In the previous lecture, we had discussed about the conservative forces. We had seen that how the work done by a conservative force on a system can be represented by the change in the potential energy of the system. Later on, we had seen that if a mechanical system is in equilibrium and the virtual works on that system are due to only the active forces, which the active forces are the conservative forces or the potential forces, then for that system, okay, where the virtual works will be only due to the potential forces or the conservative forces, and if that system is in equilibrium, we can say that the change in the potential energy of that system should be zero. And later on, we had modified this equation. We had written this equation that the change in the potential energy of the system with respect to any independent coordinate should be zero. Okay, so if we consider our mechanical system to be a single degree freedom system, okay, if the mechanical system is considered to be a single degree freedom system, then we can say that the complete motion or the complete configuration of that system can be represented by an single independent coordinate theta. Okay, and for the equilibrium of that system, the change in the potential energy, the derivative of the potential energy with respect to that independent coordinate should be zero. Okay, so therefore we are now interested in finding this y as a function of, rather we are interested in finding this potential energy as a function of this independent coordinate theta. Okay, so once we establish the potential energy of a system as a function of an independent coordinate theta, okay, this independent coordinate is sometimes represented in terms of x, sometimes in terms of y, sometimes different x represented by q, and sometimes it is also represented in terms of theta. Okay, that I had discussed in the previous lecture. Therefore, our main goal is to establish the potential energy of a system in the function of that independent variable. Okay, and later on we can differentiate that potential energy function with respect to that independent coordinate, and once we equate it to zero, we will get the condition of the equilibrium. Now before finding this, before writing the equation of the potential energy of any system, we must know about the sign convention of the potential energy of the gravitational force and the potential energy of the elastic force. Now you can see a text here, or rather a schematic which has been taken from the Merriam-Greek text. There is a object, okay, there is a datum plane. Okay, you can see that there is a datum plane, and on that datum plane we take the gravitational potential energy to be zero. Okay, we select an arbitrary, okay, this datum plane is an arbitrary plane. The choice of this datum plane is arbitrary. We can select it anywhere where we want, and the potential energy of the system on that datum plane is taken to be zero. Now if our system or an object lies above this datum plane, you can see that currently this body is lying at at a height of h, okay, above the datum plane. Then in this case we can see that the gravitational potential energy will be equal to wh, and it will be positive because the body is at a distance of h above the datum plane, therefore its gravitational energy is positive, and that is equal to plus wh. And when the body or an object is lying below the datum plane, now in this case you can see that this object is lying at a distance of h but below the datum plane, then its gravitational potential energy is taken to be negative. Okay, I have written here that body is at a distance h below the datum plane, therefore its gravitational potential energy is negative. Okay, it's represented by Vg and it is negative. So it's quite common sense that when we are taking this body from datum plane, okay, suppose this object is at datum plane here, I am displacing this body from the datum plane to a region, okay, above the datum plane. So the initial position is here on the datum plane, and the final position of the object is above the datum plane. And I have displaced this body from the datum plane above the datum plane at a distance of high h. Okay, therefore I am displacing it vertically upwards, and the displacement is equal to h. Now see here, the weight force is acting downwards, therefore I am doing work against gravity. Or in other words, I can say that the work done by the weight is negative. Work done by the weight is negative means that we are doing the work against gravity. Okay. So you can see that the weight of the object is in the downward direction and the displacement of the object is in the upward direction. Therefore, the work done by the weight is negative. And that means we are doing the work on this object in taking it from the initial position to the final position against the gravity. And that work done will get stored in the form of the gravitational potential energy. You can see that whenever the work done is negative, that work done gets, whenever the work done is negative, we say that we are doing the work on the system. And that work done on the system gets stored as the gravitational potential energy. Okay, now see here in the second case, the object is moved from the initial position of the where it is lying on the datum plane, and we have displaced it vertically downwards. Now see, weight is acting in the vertical downward direction and the displacement of the object below the datum plane is also in the vertically downward direction. Then we can say that the work done by the weight will be positive. Okay, here in this case, the work done by the weight will be positive. If I want to write the equation of the work done, that is from the initial to the final position, this will be positive, WH. When the work done is positive, that is, it has released the energy and we say that its potential energy has decreased. Okay, here the work was done and that work done was getting stored in the form of the potential energy. Therefore, the gravitational potential energy here was positive. Now here in this case, the system is doing the work, that is the work is released, hence its potential energy will get decreased. That is the capability of the doing work will get decreased because it has done the work while moving from this datum plane to a position at a distance of h below the datum plane. Okay, therefore in this case this work done is positive, while as the gravitational potential energy here in this case will be negative. Okay, it's quite obvious from the common sense. Now see here this datum plane, the choice of datum plane is arbitrary. Because we are interested in change in the gravitational potential energy. We are not interested in the absolute values of the potential energy, rather we are interested in the change in the values of the gravitational potential energy, and the change will be independent of the uh, position of the datum plane. Okay, it will be independent of the position of the datum plane. No matter where you select the datum plane, the change in the gravitational potential energy of the system when it displaces from one position to another position, that will be independent of the choice of the datum plane. Therefore this datum plane is arbitrary, therefore we can select it anywhere. Okay, it won't affect our results. Okay, so this is the sign convention regarding the gravitational potential energy. Now let's move to this elastic potential energy. So when a spring is either elongated or compressed by an amount S, okay, we have been mostly representing the extension or the compression of the spring by X. Whenever a spring is elongated or compressed by an amount of X from its unstretched position, that is the datum, the energy stored in the spring is called the elastic potential energy. This we have seen, this relation we had seen in the previous lecture. So this energy is always a positive quantity, since the spring force acting on the attached body does positive work on the body as the force returns the body to the spring's unstretched position. So what does this statement say? Okay, see here, this is the undeformed position of the spring. The block initially would have been in this position. Okay, when the spring is undeformed, the block would have been in this position. Now suppose an external force is acting on the block, which is displacing this block from this initial position and it is attaining this final position F. During this course, the stretch in the spring is equal to S. Now we can see that the work done by the spring is negative. That is, work done from initial state to the final state, that will be negative. Negative, why? Because the restoring force, okay, the work done by the restoring force is negative. Okay, the work done by the spring force is actually the work done by the restoring force, that is negative. The restoring force is acting in the negative x direction, and the displacement of the spring is in the positive direction. Okay, positive x direction. Therefore, the force and the displacement are in the opposite direction. Therefore, the work done by the spring force is negative. Okay, it's always negative because the restoring force will always be opposite to that of the displacement. But see here, the energy stored, the elastic potential energy stored will be positive. Because once we release this force F, okay, once we release this force F, the restoring force will try to move the block back to its undeformed position. In that case, the restoring force will be acting in the negative direction, and the displacement also of the block will also be in the negative x direction. Therefore, both the restoring force and the displacement of the block is in the what we call as the negative x direction. That is, they are in the same direction. Therefore, we can say that the potential energy, or rather the elastic potential energy, is positive because it is capable of doing the positive work. What does potential energy signify? It signifies the capability of doing the work. So it is positive because it is capable of doing the positive work once we release this force and the block is moved back to its original position. Therefore, reading this statement again, this energy is always a positive quantity since the spring force acting on the attached body does positive work on the body as the force returns the body to the spring's unstretched position. Okay. Similarly, we can see that the compression force in the spring. Now, this is the undeformed position of the spring. The block initially would have been in this position. Okay, the block would have been in this position. Now, what we are doing here is we are compressing the block. Okay, we are actually applying an external force in this direction, which leads to the displacement of the block from this initial position to this final position, and the corresponding compression in the spring is represented by S. Again, you can see that the work done from moving from initial to the final position, that will be negative. The work done by the spring force, okay? Because the spring restoring force will be in the positive direction. The displacement is in the negative direction and the restoring force of the spring is in the positive direction. Therefore, the work done will be negative. But again, we can see that the elastic potential energy will be positive because the spring force is now capable of doing the positive work. Because if we release this force, the restoring force will try to move this block from its deformed position back to the undeformed position. Therefore, in this case, the spring force and the displacement will be in the same direction. Therefore, we will get the positive work. Okay. So we can say that the spring force does negative work when it's when it is deformed. Okay, when it's compressed or elongated from its undeformed position. Okay, but once the external forces are released, the spring force has the capability of doing the positive work because it will try to bring the system back to its original state, or rather we can say that it will try to bring this system to the undeformed state. Okay, therefore it has a capability of doing the positive work, hence the energy stored in the spring is always the positive energy. Okay, we can say that the elastic potential energy is always a positive quantity. So we can see, once we know the sign conventions, we can also write the potential function for this system shown here. Okay, assuming that, first of all, I will make an assumption that assuming spring to be undeformed at datum. Okay, so I have assumed the spring to be undeformed at datum. So what does that mean? This means that the block is here and this is the spring. Okay, this is the block, this is the spring, and in this case And this is the total length of the spring, and this will be the undeformed length of the spring. Okay, this is the undeformed length of the spring. And now it is clearly seen that in this position, the spring is in the compressed state, and the compression of the spring is denoted by this distance y. Okay, the compression of the spring is denoted by this distance y. Okay, so actually I would like to just make a change here. Let this spring be connected to the center of gravity of the block. Okay, so this length of the spring is the undeformed length of the spring. Now it's clearly seen that in this position shown by the figure, okay, taken from the RC Blur text, the spring is compressed by an amount of y. Okay, that is, this will represent the compression in the spring. This is the compression in the spring. Okay, now see, if I want to write the potential energy of this system, the potential energy will be the summation of the gravitational potential energy and the elastic potential energy. We can see that if we have taken this to be the datum, the weight W, okay, its center of gravity is here. The center of gravity of the weight W is at a distance of y below the datum. Okay, it is at a distance of y below the datum. Therefore, what we can conclude here is that since this block is at a distance of y from the datum, below the datum, therefore the gravitational potential energy of this block here will be negative. Therefore, this gravitational potential energy can be written as minus Wy, okay, as we have seen the sign conventions in this previous slide. Okay, had this block been above the datum, then we have written the sign to be positive. And the elastic potential energy is always a positive quantity. Okay, it's undeformed at this datum, but when we are looking at this position of the system, the spring is at its deformed state, and the deformation in the spring is given by y. Therefore, the elastic potential energy in the spring will be half of ky square. Okay, so this is the total potential energy of the system. And so we can see that we have represented the potential energy of the system in terms of an independent coordinate, that is this y. Okay, so this is how we can write the potential energy of a system. Okay, so this is a very basic system. We might get some complicated systems in the question. Okay, but we must learn how to write the potential energy in the form as a function of an independent coordinate. Okay, this independent coordinate can be theta, x, y, q. Okay, currently it was a function of y. Now writing this equation again, the potential energy of this system, it is equal to minus wy plus 1 by 2 ky square. Okay, so for equilibrium, we know that the change in the potential energy of the system with respect to an independent variable or an independent coordinate should be 0. So if I differentiate the above equation, I will get that minus w plus 1 by 2, the differentiation will be 2ky. This term has to be 0. So from here we can get that minus w is equal to ky, rather minus ky, or we can say that the equilibrium position, okay, substituting y eq instead of y because this is the equilibrium position. Okay, we have already given the condition of the equilibrium, that is the change in the potential energy, the derivative should be 0, okay, with respect to this independent coordinate. So y equilibrium, it will give us the equilibrium position, that will be equal to w by k. Okay, so this is the condition which we got of the equilibrium. Okay, condition of equilibrium. Okay, so for equilibrium, this distance y should be equal to w by k. This could have also been easily seen if we had drawn the free body diagram of this block. See, the weight of this block will be acting in the vertical downward direction. Now, since this spring is in compression, it will be exerting a restoring force on this block in the upward direction. So this is the spring force. And for equilibrium, summation of the forces in the vertical down direction should be zero. Okay, vertical direction should be zero. Now spring force is acting in the vertically upward direction and the weight is acting downwards. This has to be zero. And the spring force will be denoted by ky. This has to be equal to weight. So from here we get that for equilibrium, the equilibrium position will be given by, okay, since this is a equilibrium position, okay, we have used the condition of the equilibrium. Therefore, instead of y, I write that yeq, that is equal to w by k. Okay, whether I am using the force analysis or whether I am using the criteria of the potential energy for the equilibrium, I get the same result for the equilibrium. Okay, it is clearly seen here. So now we have seen that how the potential function will help us in determining the equilibrium criteria for a system. Okay. Now this potential function not only helps us in determining the equilibrium criteria, it can also tell us about the what type of equilibrium the system is in. We can see that the equilibrium is of three types. The first type of the equilibrium is known as stable equilibrium. So let's see what is the stable equilibrium. A system is said to be in a stable equilibrium if it has a tendency to return to its original position when a small displacement is given to the system. The potential energy of the system in this case is minimum. Now let's see what is the unstable equilibrium. A system is said to be in unstable equilibrium if it has a tendency to be displaced farther away from the original equilibrium position when a small displacement is given, and the potential energy of the system in this case is maximum. Okay, to understand this statement, let's consider an example of a ring. Okay, suppose this is a ring, and in this ring, if we have a roller situated in this position, let the roller be situated in this position. Okay, now we can see that if we are giving a small displacement to the roller, either in the right direction or the left direction, let's give it a small displacement. We can see that the tendency of this roller will be to come back to its original position. Okay, it might go somewhere here. Okay, after some oscillations, it will attain its equilibrium position again. So this position of the system or the roller in this case corresponds to the minimum potential energy, and the equilibrium of the roller, okay, in this position is said to be the stable equilibrium, because if it is displaced from its initial equilibrium position, it has a tendency to come back to its original position, because this position is of the minimum potential energy. Hence, this equilibrium of the roller is said to be the stable equilibrium. On the other hand, had the roller been in this position, okay, if we are giving a small displacement to the roller, either in the clockwise or the anti-clockwise direction, the roller will never come back to its original position. Okay, it will try to attain the position of the minimum potential energy. That's why in this case we say that although the system is in equilibrium, but it is in unstable equilibrium, because once we are giving the displacement to the roller, okay, small displacement either towards right or left, it will never come back to its original position. Okay, it will try to attain the minimum potential energy, because in this case the potential energy of the roller is maximum. Okay, so unstable equilibrium corresponds to the maximum potential energy of the system. And we also have another type of equilibrium, that is the neutral equilibrium. So if it is a ground, Okay, if this is any stationary surface, and if I have a roller here, in this case, if I'm giving any displacement to the roller, it will attain another equilibrium position. Okay, but throughout this displacement, either in the right direction or in the left direction, the potential energy of this system is constant. Okay, the potential energy of the system isn't going to change. Okay, so each position, okay, each position from the original displaced position. Okay, if this is the roller here in the original position, now if we are displacing it towards the right or left, the new position will also be a equilibrium position, and in each position the potential energy of this roller will be a constant. Okay, so this third equilibrium, that is known as the neutral equilibrium, it corresponds to the constant potential energies of the system. Okay, so coming back to our PDF, so we have discussed what is the stable equilibrium with an example, and we can see that the potential energy of the system in this case is minimum. Similarly, the potential energy of the system in the case of unstable equilibrium is maximum. Okay, so dv by dx will be, or dv by d theta will be 0 for each of the equilibrium, whether it is stable, unstable, or neutral equilibrium. Okay, but what is stable and which condition of the equilibrium is unstable equilibrium, that will be determined when we take the second differential, okay, or second derivative of the potential energy function with respect to the independent coordinate theta. So let's see the definition of the neutral equilibrium. A system is said to be in neutral equilibrium, okay, if on account of the small displacements away from the original equilibrium position, a new equilibrium position are attained. Okay, the new equilibrium positions are attained, but the potential energy of the system does not change. Okay, we can see that the potential energy remains constant. Okay, so this figure has been taken from the Merriam-Craig book. You can see that if we are displacing this roller either in the right direction or in the left direction, we can see that after a few oscillations, the tendency is to come back to this original position, because this position corresponds to the minimum potential energy. Okay, this corresponds to minimum potential energy. And again, it can be clearly seen that if we are giving the displacement to the roller either in the right or left direction, this roller will never come back to its original state. Okay, because this position is corresponds to maximum potential energy. And in this case, if we are giving the displacement to the roller, it will obtain another equilibrium position, but the energy or the potential energy will remain constant. Okay, the potential energy remains constant. So these equilibrium positions, okay, so different texts have shown in a different way. So R.C. Hibbeler has taken an example of a disk which is hinged here, okay, and this Beer Johnston has explained this equilibrium criteria, okay, whether it is stable, unstable, or neutral equilibrium with the help of a rod. Okay, again you can see that if we are displacing this disk either in the clockwise or anti-clockwise direction, let's say that if we are giving a clockwise rotation to this disk, the center of gravity will try to move upwards. Okay, but this center of gravity, now the weight force will be acting here. This will be the weight force. What it will do, it will try to, okay, it will provide a torque. Okay, the weight force will provide a torque in the anti-clockwise direction. Okay, if the applied displacement is in the clockwise direction, the weight force will try to provide the torque in the anti-clockwise direction. Okay, and the tendency will be to come back to this original state. Okay, that is known as the stable equilibrium. Now in the unstable equilibrium, you can see that if we are giving a rotation in the clockwise direction, obviously after some time the center of gravity will shift here, and you can see that the weight force will be here. What is the torque provided by the weight about the hinge? the torque provided will be also in the clockwise direction. Okay, see here in this case the displacement was in the clockwise direction, but the torque will be, that is torque that is denoted by I alpha, that will be in the opposite direction. Here the displacement as well as the torque are in the same direction, therefore this will this system is in the unstable equilibrium, because it will try to attain the position of the minimum potential energy. Okay, it will never come back to its original state, because this torque is favoring this displacement. Okay, here this torque produced by the weight is opposing this displacement. And in this case of the neutral equilibrium, we can see that if we are giving the rotation either in the clockwise or anti-clockwise direction, the disk will attain and each position attained by the disk will be an equilibrium position, but its potential energy will not change. Okay, the potential energy remains constant. So one can also analyze that this corresponding position, okay, this position of the stable equilibrium corresponds to minimum potential energy. Now, if we are giving the displacement in the clockwise direction, the potential energy was getting raised. Okay, so what was its tendency? Its tendency is come back to the minimum potential energy position. That is why it comes back to its original stable equilibrium position. And now in this case, when we are giving the displacement or the rotation, okay, the potential energy does not change. Okay, it remains constant. Every position is a equilibrium position. Okay, but the potential energy isn't changing. And if we see this case, okay, if we are seeing in this case, the body was originally in the unstable equilibrium, the potential energy, this corresponds to the maximum potential energy state. And after giving some displacement, the potential energy just decreases. Okay, it starts decreasing unless and until, and it keeps on decreasing unless and until it does not attain this stable equilibrium position. Okay, now one more thing here in this Beer-Johnston text, this stability has been explained by the example of this rod. If we are displacing this rod, okay, it is also common experience. In this case, the rod is hinged. Okay, the rod is hinged here, and okay, the rod is hinged at the top. And if we are giving displacement, suppose in the anti-clockwise direction, as has been shown in this figure, what will happen? The weight will produce a moment or a torque about the hinge A. Okay, there will be a moment due to this weight force about the hinge A, which will try to restore this. Okay, that is this torque will try to restore this, that is equal to I alpha, and this is the displacement. Okay, this is the displacement in delta theta. Okay, d theta or theta in simple terms. So the displacement was in the anti-clockwise direction, and the torque due to this weight about hinge A will be in the clockwise direction. Therefore, any displacement from this stable position will try to increase the potential energy of the system or of the rod, but the tendency of the system will be to come back to this original minimum potential energy position, that is the position of the stable equilibrium. Now, in this case, this rod is again being given a displacement in the clockwise direction, and what is happening here, this weight is producing a moment or a torque about hinge A. Okay, and it is in the same direction as that of the displacement. So unless and until it does not obtain the stable equilibrium position, okay, it will keep on falling down. Okay, the final equilibrium position, the rod will look like this. Okay, so as is in this case, okay, it will attain the same equilibrium position, which is the state of the rod shown in this figure. Okay, and see here in the last case, this is the position of the neutral equilibrium. Okay, you can see that in this position, the rod was hinged at one end of the rod, the rod is hinged at another end of the rod. But here in this case, the rod is hinged at the center of gravity. And if this is a homogeneous bar, then we can say that if we take this portion to be having weight W by 2, okay, if this is the total length is equal to A, sorry, the total length of the rod is equal to 2A, then this portion of this rod will have the length of A, this will have length of A. What will be the weight if this is the homogeneous bar? Then the weight of this portion will be here, that will be W by 2, and the weight of this homogeneous bar will be here, of this portion, okay, of the second half of the portion of the rod will be in this direction. So this portion will try to create a clockwise movement, okay, rather anti-clockwise movement, and this will try to create a clockwise movement. So any displacement will be, okay, so if we are displacing this rod, and it will attain this position after some time, okay, sometimes after some time this rod might attain this position, okay. So every position attained is an equilibrium position. The rod attains every position attained by the rod will be an equilibrium position, and in every position the potential energy of the rod will remain same, okay, it won't change. So this is the discussion regarding the stability of the equilibrium, okay. Now how can this potential energy function help us to find the stability of the equilibrium? If we draw a curve between here, if we have an independent coordinate, suppose theta, and this is the potential energy, okay, so we can see that the potential energy is a function of theta. Suppose the potential energy of a system is varying in this manner, okay, the graph between the potential energy with respect to an independent coordinate theta for a system is shown by this figure, okay. So we know that for equilibrium dv by dx should be 0. That is, body will be in equilibrium at those points where the slope of this potential energy versus theta curve, okay, I can put here theta instead of x, as I have represented the independent coordinate by theta. So all those positions where the slope will be equal to 0, those will correspond to the equilibrium positions, okay, they will correspond to the equilibrium position. So first of all, we can see that this position, okay, this position here, if we draw the slope, sorry, if we draw the tangent, okay, if we draw the tangent, the slope of the tangent is 0. Similarly, in this, at this point, if we draw a tangent, the slope of the tangent is 0. And here you can see that this potential energy function is a constant. Therefore, its slope is equal to 0. That is, dv by dx is, or rather dv by d theta is 0. In this case, at this point, dv by d theta is also 0. And at this point, dv by d theta is 0. So which positions correspond to the maximum? So all these positions are, first of all, the equilibrium positions, okay? Therefore, we can see that at this value of theta, suppose this is theta 1, this value of theta, suppose it is theta 2. And when the position of the system is given by this value of theta, okay, over a range, okay? So all these positions are the equilibrium positions for the system. Now, which will correspond to the stable equilibrium and which will correspond to the unstable equilibrium, that will be given by the second derivative. So since the dv by d theta is 0, therefore this is a position of equilibrium, but this corresponds to the minimum equilibrium. Okay, you can see that this corresponds to the minimum potential energy, and this point corresponds to the maximum potential energy. So what is the criteria for the maxima and minima? Okay, what is the criteria for the maxima and minima? Since this corresponds to the minimum potential energy, we know that for minimum, the second derivative of this function should be greater than 0. That is, d square by, that is the second derivative of the potential energy function with respect to theta should be greater than 0, because it is the condition of minima. Whereas in this case, the potential energy is maximum, okay? The potential energy is maximum. Although the slope is 0, but the potential energy is maximum. And what is the condition of maxima? The condition of maxima is that this second derivative, okay, should be, from the basic calculus, we know that the second derivative of the potential energy function with respect to theta should be less than 0. Okay, that is, it should be negative here and it should be positive here. For the condition of minima, this derivative should be greater than 0. Okay, because the minimum potential energy corresponds to stable equilibrium. Okay, so this condition is actually the condition for stable equilibrium. Okay, so dv by d theta is equal to 0. That gives us the criteria for the equilibrium, and to calculate or to find whether the body is in stable or unstable equilibrium, we have to calculate the second derivative of the potential energy function with respect to theta. So this position here corresponds to unstable equilibrium. And if the potential energy is remaining constant, then we know that this corresponds to neutral equilibrium. Okay, this region corresponds to neutral equilibrium. Okay, so what can we can summarize these things. If dv by dx or dv by d theta, that is the first derivative of the potential energy with respect to the coordinate theta, is equal to 0, and d square v, that is the second derivative of the potential energy function with respect to theta, is greater than 0. So this gives us the condition for stable equilibrium. And what is the condition for unstable equilibrium? The condition for the unstable equilibrium is, first of all, dv by d theta should be 0. It is the condition for every type of equilibrium. And for the unstable equilibrium, we can say that the second derivative of this potential energy function with respect to theta should be less than 0, because this is the condition for the maxima, and the potential energy is maximum when the system is in the unstable equilibrium. Now let's see what is the condition for the neutral equilibrium. Okay, for the neutral equilibrium, what do we have to do? So let's read the statement first. If both the first and the second derivative of a potential energy function are 0, it is necessary to examine the derivatives of the higher order to determine whether the equilibrium is stable, unstable, or neutral equilibrium. Okay, so if this d square by the second derivative of the if the second derivative of this potential energy function comes out to be negative, rather positive, okay, it is the case of the stable equilibrium. And if the second order derivative comes out to be negative, then it is the case of maxima. The maximum potential energy corresponds to the unstable equilibrium. Now similarly, the statement is here, if the first and second derivative are both 0, okay, it is necessary to examine the higher derivatives. That is, the equilibrium is neutral if all the derivatives are 0, since the potential energy is then a constant. Okay, what will happen in the case of neutral equilibrium? dv by d theta, that is equal to d square v by d theta square. Okay, the third derivative of the potential energy function, and so on. If they all come to 0, then the system is in neutral equilibrium. Okay, so we can read the statement again. If the first and the second both are 0, it is necessary to examine the derivatives of a higher order to determine whether the equilibrium is stable, unstable, or neutral. Okay, the equilibrium is neutral if all the derivatives are 0, since the potential energy is then a constant. The equilibrium is stable if the first derivative found to be different from 0 is of the even order and positive. Okay, in all the cases the equilibrium will be unstable. Okay, so these are the conditions for the equilibrium, or rather the stability of the equilibrium. Okay, now let's take an example of a rod here. Okay, so the previous text was from B. Johnston. Okay, both the above and the below text. Now let's conclude this lecture by finally taking an example of a rod. Okay, so the source of it is the textbook by Bedford Fowler. Okay, so see the example of this rod. There is a hinge. Okay, there is a rod. It is hinged at this position. Okay, you can see that there is a rod. It is hinged at this position, and it is making an angle of alpha with the vertical. Okay, it's making an alpha with the vertical. So if we see its center of gravity, the center of gravity of this rod will be lying somewhere here. Assuming this to be the homogeneous rod, then this distance will be equal to alpha by 2. This will be L by 2, and this length, okay, from the center of gravity to the other end of the rod, that will be also L by 2. Okay, this angle is alpha, therefore this angle will also be equal to alpha. So I can draw a right angle triangle where this point is the hinge. Okay, let's say that this is A, this is hinge A, this is the center of gravity of the rod, and this distance is equal to L by 2, and this is the angle alpha. Okay, I written theta, this is the angle alpha as per the text. So if we write the potential energy function of this rod, okay, if we write the potential energy function, we can see that the potential energy will be only the gravitational potential energy. Okay, this will be only the gravitational potential energy because the spring is missing. Okay, there isn't any elastic potential energy term because there isn't any spring attached to it. So the gravitational potential energy, for that we need to consider a datum, and the datum has been considered a horizontal plane passing through this hinge. So we can see that if W is the weight of the rod, the gravitational potential energy will be equal to the weight of the rod and the vertical distance of the center of gravity from the datum. You can see that the datum is here. The center of gravity of this rod is lying at a distance of, okay, this is the distance of the center of gravity of the rod from the datum. And from this right angle triangle, you can clearly see that this is equal to L by 2 cos alpha. Okay, this distance will be L by 2 sin alpha, and this will be L by 2 cos alpha. Okay, I'll write it again. It is equal to L by 2 cos alpha. The vertical position of the center of gravity from the datum, okay, it is equal to L by 2 cos alpha. So this is the weight, and its distance from the center of gravity distance, the distance of the center of gravity from this datum is equal to L by 2 cos alpha. And since this center of gravity is located below the datum, okay, we had seen the sign conventions previously. Since it is located below the datum, therefore this potential energy will be negative. So here see that this potential energy is a function of an independent coordinate alpha. This alpha is enough to determine the position of all the, okay, it will determine the position, each position. Okay, there isn't any other coordinate to specify the position of this rod. Okay, so we can see that this is a single degree freedom system because this alpha is alone sufficient to determine the every position of the rod. Okay, so we can see that if alpha is equal to 0, this rod is completely vertical. If alpha is equal to 90, this rod is completely horizontal. Okay, now if we apply the criteria of equilibrium to this rod, the first derivative of the potential energy function with respect to alpha, okay, it is equal to 0. Now after differentiating this, we will get that W L by 2, the differential of this will be minus sine alpha. This will be 0. And we can say that W L by 2 minus and minus will be plus, and this will be equal to 0. Okay, so what is the condition of the equilibrium? Now we can see that W and L can't be 0. Therefore, from here we can conclude that the equilibrium will be given by the condition of the equilibrium will be given by sine alpha equal to 0. And from here we can see that sine alpha will be 0 when alpha is 0 degree and it is equal to 180 degree. Okay, so sine equal to 360 will again be the same, that is it will again be equal to sine, okay, alpha equal to 0. Okay, it will be in the same position in which alpha is 0. Okay, so if we clearly see this, when sine alpha is 0, or we get that alpha is 0, so this position has been shown where alpha is 0. See, this position is of the stable equilibrium. First of all, this position is of the equilibrium. Okay, isn't it? We had seen in the previous text as well, this corresponds to an equilibrium position. And this position, okay, this should be the stable equilibrium position, because any displacement from this position will try to bring the system back to its original position. So this should definitely correspond to the stable equilibrium. And again, you see that sine alpha is 0 when alpha is also equal to 180 degree. So this angle, this position of the rod corresponds to this alpha is equal to 180 degree. But we have seen in the previous slide that this should correspond to the position of unstable equilibrium. Okay, so there will be two equilibrium positions. One will be alpha is equal to 0. Okay, when alpha is equal to 0, that is this position of the equilibrium. And second equilibrium position will be when alpha is equal to 180 degree. Okay, in both the cases, sine alpha will be 0. That is the derivative of the potential energy function with respect to alpha, that will be 0. Okay, now we have seen that dv by d alpha, this first derivative of the potential energy function with respect to alpha, is equal to WL by 2 sine alpha. Okay, to see whether the system is in equilibrium or is in stable or unstable equilibrium. Okay, remember we have to check for alpha is equal to 0 and alpha is equal to 180 degree. Therefore, we need to calculate the second derivative, that is d square v by d alpha square. This has to be equal to, this will be equal to WL by 2 cos alpha. Okay, now if alpha is 0, if I substitute alpha to be 0, I will get that d square v by d alpha square. This will be equal to WL by 2, because cos alpha, that is cos 0, will be 1. Okay, so this term is positive. And we have seen that when the second derivative of the potential energy function with respect to alpha is a positive, it corresponds to what? It corresponds to stable equilibrium. Stable equilibrium. And positive, when the second derivative is positive, we say that it is the position of the minimum potential energy. And if we take alpha to be, if we put in the second derivative, alpha is equal to 180 degree, we will see that d square v by d alpha square, this will be equal to cos of 180 will be -1. Therefore, we will get minus WL by 2. And this result is negative, which means that when the second derivative is negative, the body is in unstable equilibrium, or it corresponds to the case of maximum potential energy. And finally, all these results can be plotted on a graph. Okay, so the first graph represents the variation of the potential energy with the alpha. Okay, so if you remember, it was given by the variation of the potential energy with alpha was given by minus WL by 2. I think it was sine alpha, or rather cos alpha. Okay, it was cos alpha. Okay, minus WL by 2 cos alpha. And the variation of the first derivative with alpha was given by WL by 2 sine alpha. Okay, and the variation of the, that is the second derivative of the potential energy function. Okay, if we plot the second derivative, the function was, we had seen lastly, it was equal to WL by 2 cos alpha. So all these have been plotted here. Since potential energy is minimum in this case, okay, this is the variation of the potential energy over a length, okay, over a length of alpha sum. So this position corresponds to the unstable equilibrium because the potential energy is maximum. This position corresponds to the stable equilibrium because the potential energy is minimum. Okay, this variation gives us, this is the variation of dV by d alpha, and when dV by d alpha is 0, those are the points of equilibrium. Okay, see here, this point should be of the equilibrium because dV by d alpha is 0, and this point is also equilibrium point because dV by d alpha is 0, and here alpha was equal to 0 degree, and here alpha was equal to pi degrees, or we can see that 180 degree. And the third, okay, the third graph is for the second derivative of the potential energy function with respect to alpha. So this will be the curve. Okay, and in this case, this point is what? This point is a positive. Okay, when the second derivative is positive, when second derivative is positive, that corresponds to the stable equilibrium, and when the second derivative is negative, it corresponds to the unstable equilibrium. Okay, so this ends all the theory portion regarding this potential energy criteria and the stability. In the upcoming lectures, we will solve some few problems, okay, and we'll conclude the course. Okay, thank you.